All right, so the first recording of the new year. Happy 2021, you guys. We made it, and now we're back to where we were. Anyway, I'm going to do a quick little recap of where we left off with using definite integrals. As you can see on my screen, we're going to be talking about definite integrals in this section as well as antiderivatives. Now, last chapter, there was a little bit on antiderivatives, and I chose to skip it because it wasn't really applicable at that point in time. It will now become applicable. So I just wanted to review what a definite integral was, just in case for some weird reason we might have forgotten over the last couple of weeks. So first of all, what is a definite integral? So to review, we had that elongated S. That was the symbol for an integral. And then we had a number on the bottom and a number at the top. In this section, we're going to use a lot of the A and the B for being the lower and the upper bound. So what is a definite integral? The area under a curve on a closed interval, A to B. Now, how have we evaluated definite integrals? Well, we've used the rectangular approximation method. So we had the right rectangular approximation method. That's when the upper right-hand corner of each rectangle was touching the curve. That was the height of the rectangle. We had the LRAM, which is the left rectangular approximation method. That's when the upper left corner is touching the curve. And then we had the MRAM, which was the midpoint rectangular approximation method, and that's when the middle of the rectangle was touching the curve, which is arguably the most exact for the general usage. But as many of you found out, that the MRAM, even though it's more exact, was a little bit more tedious because we wanted a nice interval at the bottom, and so that meant that the value in between usually was a decimal. We can fix that by having a wider rectangle. Maybe it's by 2 units, so the middle would be even units, but that's just something to experiment with. And then after we use the RAM, the rectangular approximation method, we progressed into trying to fit geometric shapes under the curve. So maybe we noticed that it was a semicircle or a triangle or a rectangle or a trapezoid or things like that. And so we use geometric shapes and their formulas to fit under the curve to approximate. So what we're going to be progressing onto is just being able to look at the definite integral, use antiderivatives, and then mathematically calculate the area under the curve without having to draw any shapes or use any formulas. Now, with the integrals, we are going to have some rules. The first 5 are pretty important and applicable. The last 2 are going to be more of a broader conversation, and they might and probably will seem like common sense. So we're not actually going to be using the last 2. It's just kind of like it's going to naturally happen, so we had to state it to be true. It has to be a rule, kind of like gravity. Gravity is a rule on Earth. I might explain gravity to you, but we live it every single day. If I pick up an object and drop it, it will fall. So that's kind of the relation I'm going to make to the last 2 rules. You're going to read them and be like, yeah, that makes sense. So the ones that may not. So the first rule that we're going to talk about is going to be the order of integration. Now, all of our integrals that we calculated with those shapes, we tend to start at the origin and then progress to the right. Well, we can also go to the left. We can go in the negative direction. And so what this is saying is that if we're going from our upper bound to our lower bound, so we're starting at the highest value and going to the lowest value, instead of calculating that, because technically an integral should go from a min to a max, we can go ahead and flip that and then just take the negative of it because we're going in the other direction. So the negative of the integral of f of x is the same thing as going from the largest to the smallest value. The 0 rule. If you're going from one place and ending at that place, you have gone nowhere. So the value from A to A would be 0, because if you haven't gone anywhere, you wouldn't have traveled any distance, you wouldn't have covered any area, so it would have to have a value of 0. My personal favorite, the constant multiple rule. This works the same way it did when we were taking derivatives. Many times I'd say, yeah, you could use that pi, you could use that fraction, but what if you just take it out, do the derivative, and then multiply it back in? It works the same way with integrals. So if you have an integral from a to b, and it's some constant, 2, 3, pi, whatever it may be, something that is a definitive number that isn't going to change, it's not a variable, and that is multiplying a function, you can go ahead and take that constant out, find the integral, and then multiply by it. Sum and difference, if you are adding two functions that are on the same interval, so f of x is going from a to b and g of x is going from a to b, you are free to break it up into two integrals, evaluate each one, and then add or subtract them. So you do not have to worry about combining functions and then evaluating them. Evaluate them first and then combine them. Additivity. Additivity is a kind of cool one. It reminds me of completely blanking it, the transitive property. Monday, am I right? So additivity is saying that if you have a function from a to b, and you have the same function from b to c, you can go ahead and add them together, and that will be equivalent from a to c. So here it is, f of x dx from a to b, b to c. Since it's the same function, the same variable, and I am combining these two intervals into one bigger interval. So those are the 5 rules that we are going to be using today. The next 2 are the ones that are kind of like, yeah, that makes sense. So the first one is the max-min inequality. So if the max f, so the maximum of a function, and the minimum of a function are the maximum and minimum values of f on a to b, then we can say that if you were to take the minimum value and multiply it by the difference of the b minus a, that is going to be a smaller value than if you were to evaluate the function from a to b, which will be a smaller value than if you took the maximum of b minus a. We're going to be using this later on. This one isn't as intuitive, but the big idea is that the minimum is going to be less than the actual evaluation or equal to, and then the max is going to be bigger than the actual evaluation or equal to. And this just has a cool name. The 7th rule is called domination. So what domination is saying is that if f of x is already bigger than g of x on a to b, then the areas under their curves, respectively, will follow suit. So if f of x is bigger than g of x, the area under the curve of f of x will be bigger than the area under the curve of g of x. And then if f of x is bigger than 0 on a to b, then the integral itself must also be bigger than 0. Remember, when we take these integrals, they could be going above and below the x-axis, the horizontal axis. So it is possible to have some negative areas and some positive areas. If the overall value of the function is greater than or equal to 0, then when we add and subtract those positive and negative areas, they will also result in something bigger than 0. So that's just the domination rule. Now, these 2 rules I wouldn't worry too much about. Like I said, it's the first 5 that we're going to work on today. And here is how we are going to use them. So some examples, suppose we have the function f of x dx from -1 to 1. Let's just say that whatever this function is, if I were to add up the infinite number of rectangles or fit a geometric shape underneath, or however we approximate it, the value is 5. And then that same function from 1 to 4 is -2. So most of the function was underneath the horizontal axis. And then the last one, I switched it up and I said, what if I had h of x from -1 to 1, and that function just so happened to equal 7. So this is known information. It's not up for debate. It is what it is. Now, knowing what I supposed, I'm going to find each of the following integrals if it's at all possible. Now, the first one is I want to find the value of f of x from 4 to 1. Now, looking at the information I know, none of these go from 4 to 1. However, I can use one of my rules, the order of integration, and that says that I can flip this integral and just take the negative value of it. So if I know that from 1 to 4 is 2, I can say that from 1 to 4 is going to be the negative of -2. Sorry, I misspoke earlier. So the answer, the evaluation of A, would just be 2. What if I wanted to go from -1 to 4? Well, looking, I don't have -1 to 4, but what I do have is I have from -1 to 1 and from 1 to 4. So I'm going to use that additivity, and I'm going to go ahead and combine those two integrals. So I'm going to take from -1 to 1, I know to equal 5. 1 to 4 is equal to -2. So if I add those together, I get 3. And this last one, this is going from -1 to 1. And I'm using the f of x and the h of x functions. Now, in order to be able to do this, both of these functions would have to go from -1 to 1, which they do. That's good. So now what I'm going to do is I'm going to take my f of x function and apply my multiplier to it and do the same thing with the h of x function. So I took my multipliers out, evaluated each function. This one equaled 5. This one equaled 7. So when I multiply 2 and 5 together, I get 10. 3 and 7, I get 21. Add them together, I get 31. These next three. What if I wanted to evaluate the f of x function, the integral from 0 to 1? Well, I have from -1 to 1, so I might think it's 2.5. However, we don't know what this function looks like at all. I have no idea where it's positive, where it's negative, anything. I don't even know if it's symmetrical. So we cannot break it up. We only know what we're told. There's only 3 things that I know, that this one's 5, this one's -2, and that one's 7. I cannot assume anything else. So since I do not have an integral from 0 to 1, I can say that I do not have enough information to evaluate this integral. That's it, done. All right, how about the h of x function from -2 to 2? Well, the only thing I know is from -1 to 1. I have no idea what this h of x function does outside of that interval. I only know that it has a value of 7 within -1 to 1. So since I do not know anything outside of -1 to 1, this one is also not enough information. And lastly, f of x plus h of x from -1 to 4. Well, I know that the f of x function from -1 to 4 is 3, so I can do that just fine. However, the h of x function, I only know it from -1 to 1. I do not know what it is from 1 to 4. I cannot guess, I cannot speculate, because it's just h of x. I have no idea what it looks like. So once again, there's not enough information. So your work today is just going to be using these rules. It's going to be set up the same way. You are going to be given some information that you are to suppose, and then given that information, evaluate the integrals if it is at all possible. If you have any questions, come on into Zoom. Good luck. And hopefully you saw my note in the stream. That is that if you are a full remote student, I know we have a few in this class, the expectation for you to come in for finals will not be there. You do not need to come in for finals if you are fully remote. So if you have any questions with that, let me know. I think on Wednesday, we're gonna hear more about it, so hopefully I have more information. If you have any questions or concerns, let me know so I can bring them up and hopefully get answers for you. All right.